place for removing the latent heat of vaporization as we are creating small bubbles. So small bubbles are good because we are removing more heat because of an additional process. Why shouldn't big bubbles be even better? What do we not like about big bubbles that we're particularly fond of for small ones?
They create a film over it.
That's right, they create an insulating vapor blanket over the surface of the fuel rod. So we like operating in this region, but we have to be very careful about operating too far to this point because although this is shown as a solid line, in reality, experimentally, it's very, very difficult to get that part of the graph experimentally. What you actually do is jump over from this region straight across to this region here, and you get a very large corresponding jump in the temperature that the fuel rod operates at. That's fine if you expect that to happen, as in a boiling water reactor. It's not so good if you're designing your fuel rod to operate at these kinds of temperatures down here.
In the dip, is it the bubble is insulating it, then as you put more energy in, that sort of allows the...
Yeah, it does. The dip is, every year I say the same thing, and every year I forget to do it. I should show this dip region actually as a dotted line, because experimentally you can persuade the fluid to undergo that region, but in reality what happens most of the time is that you actually jump across from operating here straight across to operating here. This region is highly unstable and very difficult actually to reproduce experimentally. What you tend to do is go merrily up the curve to here, and then you fall off the edge of the cliff and go straight to here. And you get a corresponding large, unexpected jump in the temperature at which your fuel rods are operating. So why do we not want to operate there? Well, here it is. Exceeding the critical heat flux results in a rapid increase in rod surface temperature. And if you stay there, then that will cause you accelerated corrosion rates and possibly even coolant boiling, which is something we want to avoid. So a pretty nice simple question. Quick roller coaster graph. Critical heat flux is the peak of that first point on the roller coaster, and that's the point that we want to avoid going beyond. So for safety reasons, we operate a comfortable distance below that point. And although this particular question isn't asking it, I might have gone on to ask, well, how do we ensure that? How do we ensure we operate far away from that point? And you might be well advised to recall the departure from nuclear boiling ratio as to what it is and what typical values we might operate at. We're actually straying a little bit into the thermal hydraulics lecture here, so forgive me, but for water-cooled reactors, this is a very, very, very important point to get across. I'm very fond of this question. I'm not saying it's going to come up this time, but I actually quite like it. And you should be fond of it as well, because it's easy to remember. What principles underpin the design of reactor safety systems? If you can remember the acronym DRIFT, then you'll be in good state. Remember, if I want to avoid my trousers falling down, I've got a number of options open to me. I can go for diversity, which would be belts and braces, two completely different systems. I can go for redundancy, which is two pairs of braces or two sets of belts. So I'm using multiple components, the same components but multiple instances of them. We want our components to be independent, so the operation of my belts does not influence the operation of my braces. They're completely separate systems, independent systems. What they are not is fail-safe. If my belt or my braces fails, then my trousers will fall down. Everything becomes lost at that point. We want our systems to fail in a safe way. So if our valve, if the purpose of our valve is to introduce large quantities of cooling water, replacement cooling water, into the reactor system, then if that valve is going to fail, we want it to fail open, not closed. So we want the systems to fail in a safe way. Okay. And finally, we want our systems to be testable. Does anybody remember an example of a system that was used, that has been used for many, many years in British reactors that was not testable? Please.
Boron dust.
Boron dust in the Magnox stations, yes. The the secondary shutdown system in many magnox stations was boron dust. It probably would have operated very well, but we don't know because we were never able to test it, not fully anyway, in a full operating station, because we would not have been able to recover the dust. So if you can remember that, diverse, redundant, independent, fail-safe and testable, easy box. A little bit on nuclear fuel. Does anybody remember what is meant by the matrix fuel? Stuff that doesn't contain any fertile material. Okay, and why would we be interested in such a type of fuel? Well, if we are burning a mixed plutonium oxide, plutonium-uranium oxide, for instance, if our purpose of doing that is to remove plutonium from the face of the Earth, then we would not be doing it at the optimum rate, because although we're destroying plutonium in the reactor core, uranium-238 is also busily absorbing neutrons and turning into plutonium-239. So, although we are actually irradiating that fuel as a net burner of plutonium, we're not actually burning it at the optimum rate, because we're creating fresh plutonium at the same time that we're actually burning it. The net effect is a burning one, but it's not quite as fast as it might be. The way to get rid of that would be to get rid of the uranium. That's what we mean by a fuel that doesn't contain the fertile material. So we would replace the uranium perhaps by alumina or magnesia, some other matrix material that acts as a diluent to the plutonium but doesn't contain fertile material. What drawbacks are there? Well, there's very little Doppler feedback and relatively poor thermal properties compared with uranium oxide. That's the sort of thing we want for a matrix fuel. Just a 3 bullet point answer. Rather more long and elaborate question might be, what are the main requirements for a cladding material? And list some candidates and highlight their advantages and disadvantages. Remember, we went through a whole raft of different types of cladding material. We went through steels, zirconium alloys, ceramics, aluminium and magnesium alloys, and we identified a whole list of desirable and undesirable characteristics. So, for instance, we wanted the material to remain structurally stable under irradiation. We wanted it to be relatively resistant to corrosion and erosion and fretting damage. We wanted it to be able to have adequate fatigue strength, because sometimes we don't operate our reactors at constant power, sometimes we cycle in power and that gives rise to fatigue damage. We don't want it to gobble up neutrons, just as with the coolant, we don't want our cladding material to gobble up excessive numbers of neutrons, because we have to pay for those, we have to increase the enrichment. And just as with our coolant, we want to avoid materials which will become unduly activated under irradiation. That's particularly important for the handling of intermediate level wastes that arises when we do reprocessing. We'll be talking about it in a few slides' time. So all I'm looking for there is a few examples of what we want our cladding material to do and what we don't want it to do, and then to stack up the alternatives against those different requirements and evaluate them. So steels, remember, have very good mechanical properties. We like steels, we've been using them a long time, we understand them, a lot about their behaviour. They're very, very good at corrosion resistance, but they have a relatively high neutron capture cross-section. So we can use them, but if we're going to use them, then we have to use a correspondingly higher enrichment than we would otherwise have to use, and that costs money. Zirconium alloys also have pretty good mechanical properties, not quite as good as steel, but good nonetheless. Very, very good corrosion resistance in water environments, not quite so good in other environments, but in water they're excellent. And this is the key one, a very low neutron capture cross-section. But they're not cheap. We have to pay a lot of money to produce nuclear grade zirconium. Can anybody remember what we have to remove from it in order to make it nuclear grade?
Hafnium.
Oh, very good. Yes, hafnium. Hafnium is such a bad, or depending on your point of view, such a good new capturer of neutrons that we use it as a component in control rods. In fact, sadly for us, it occurs naturally alongside zirconium. so we have to remove one from the other, and that costs quite a bit of money. But the prize for doing so is that the resulting pure zirconium has a very low capture cross-section for neutrons, and we're able to save money by specifying a correspondingly lower enrichment patch. We could use ceramic claddings. They've got very, very high temperature capability, but very poor, very low fracture toughness and low strength in tension. So they're really only suitable for particular types of fuel, particularly all ceramic fuels, coated fuel, triso-coated fuel particles. And in the past we have used alloys of magnesium and aluminium, in fact, and still continue to do so in research reactors. They have very low capture cross-sections for neutrons, but poor corrosion resistance generally. And that limits the temperatures at which we can operate our reactors. Okay, nothing new there, just a regurgitation of what's pretty much in the notes. Steady state temperature distribution, we've gone through this ad nauseum. We know that the highest temperatures are in the middle of the pellet. We have this parabolic profile down towards the edge of the pellet. Quite a large temperature drop across the gap. Why is that? Why is the temperature drop so high across the gap, given that the gap is so very, very small? What's in the gap? Gas, yeah. Do you remember which one? Helium, yeah, absolutely. Helium, for the most part, is in the gap. There's also a little bit of air because we don't vacuum it out before we manufacture the rods. So there's roughly an atmosphere, or 1 atmospheric pressure of air in there as well. But there's about 30 bar of helium, roughly. Very small temperature drop across the cladding because it's a metal and a good conductor. And if the cladding has been in the reactor for a while, then it's accumulated an oxide there on the outside, so there's a small temperature drop across the oxide there. What about the volumetric change of fuel pellet when we put it into the reactor? You may remember, but if you don't, you can look at the diagram, that there are 2 major components to the volumetric change in the fuel as it goes throughout its life, as burning increases. One is due to the fact that every time we undergo fission, we're replacing a single uranium atom with at least 2 different fission products. One of those fission products can sit at the same lattice site that the uranium left behind, the other can't. There's no room for it, so it's forced into interstitial positions, and that causes the fuel to swell. And that swelling is pretty much linear with burn and goes on all the way through the fuel's life. The other component is densification. Remember, that's the closure of the little pores that we deliberately put into the fuel when we manufacture it. Why do we deliberately put porosity into the fuel when we make it? Almost to actually keep the gases in. Ideally, we would like all of the fission gases that are produced when we irradiate fuel to be locked inside that fuel pellet and never to escape. We never quite get there, but we get there to quite a good extent. Most fuel accommodates 98–99% of the fission gases that are generated. But they have to have somewhere to go. That place that the gases go is in the small bubbles that are left when we actually make the fuel. So we deliberately don't make it 100% dense. We aim for about 95% dense. So about 5% of the fuel, when it's made, is pores, small pores. Trouble is, when we put it in the reactor, that densification process that was initiated when we made the fuel continues. So those pores, at least the small ones, continue to densify. That process doesn't go on forever. Why doesn't it go on forever?
You can't just keep on getting denser and denser.
You can't, yeah. There's only 5% porosity in there anyway. So we can't carry on densifying it. Eventually, we will get 100% dense. What actually happens is that we fairly quickly get rid of the population of very small pores, typically 5 microns or less, and we're left eventually with a structure of fairly large spherical stable pores, typically 10–15 microns or so higher. So this densification plot, it starts quite rapidly, but then tails off and becomes almost flat towards the end of life. The net swelling rate is just the addition of those two lines. So we get an additional shrinkage of the pellet. That shrinkage kind of stops, and then from roughly 8-9 months into the irradiation, we just get a net positive swelling rate. And at some point, the pellet's volume will become equal again to its original volume, and from there on in, it just keeps getting bigger and bigger and bigger. How does fuel fail? A whole bunch of different ways, it turns out, some of which are listed there. The question might invite you to describe a number of different ways. It might be 4 or 5 or 6. I've listed rather more than those there. Sometimes we make it wrong. It doesn't happen very often, but we do. Today we make the fuel incorrectly sometimes, so manufacturing defects are a source of error. The cladding will corrode. Corrosion is the process of taking up oxygen by the cladding, so the water is reduced, hydrogen is liberated, and you might remember that zirconium has a particular affinity for hydrogen. It's like a sponge, it sucks it up. It won't do that indefinitely. If we continue to add hydrogen to zirconium metal, then it's a bit like adding sugar to tea. Eventually, the hydrogen will become saturated in the metal. The metal will become saturated, and little flakes of zirconium hydride are precipitated out, a little bit like cornflakes under the microscope. They destroy the crystal structure of the metal, and they act as cracking sites. So primary hydriding is something that we get when eventually we have too much hydrogen in the metal, and it precipitates out as flakes of zirconium hydride. The two types of fretting that we can get, debris fretting and grid to rod fretting. Remember that the rods are held in place by grids. They've got water flowing past them. These rods at a very high rate, they rattle about, or they can rattle about and flow, and they fret against the side of the grids and wear, and eventually that can wear through. Sometimes during reactor refueling operations, people leave bits in the reactor. People have left all kinds of strange things in reactors, including hammers, pliers, all kinds of things. It doesn't happen often these days, but what does happen is that people are doing electrical repair work, for example, over the refueling pond, and little bits of wire fall down into the reactor core. The grids, unfortunately, act as very, very effective sieves. And these little bits of wires get caught up in the grids, they vibrate in the flow, and they can fret or wear away at the cladding. So two different types of fretting where can take place. Pellet cladding interaction is pretty much what it says on the tin. It's the interaction stresses between the pellet, which is relatively hard, and the cladding. That can be accelerated by the presence of corrodants, typically the halogens, and unfortunately for us we get quite a bit of iodine produced. So iodine tends to accelerate that cracking corrosion mechanism. Sometimes when cladding collapses, a particular instance of a manufacturing defect, it occurs when, for various reasons, we have a gap in the stack of pellets. The cladding can collapse into that gap. We get very high strains around the edges of that collapsed region, those plastic hinges, and the cladding can fail in that way. Rod bow is simply the effect that we get when we fail to remember that zirconium alloys grow due to irradiation. Pretty much the same way that graphite does. It's a very similar crystalline structure. It's a close hexagonal structure, and you tend to get shrinkage in one direction and growth in another. That's fine if you take account of that at the design stage, but if you don't, then you can find that the fuel rod has actually contacted the bottom of the top of the bottom nozzle and the underneath of the top nozzle, and continues to grow. It runs out of space, and it bows like that. You get two adjacent rods both bowing, then they can touch. The coolant channel between them becomes starved of coolant, and the rod surface temperatures increase, and we get all these other things like corrosion and hydroding and so on. And if we operate beyond that critical heat flux, of course, then we depart from nuclear boiling, and we can get a phenomenon called raying. And again, that gives us accelerated corrosion and hydroding. So a whole bunch of different mechanisms there. You're not expected to remember them all, typically just a handful. How do we make processes that we went through to actually manufacture nuclear fuel. But all we're interested in for the IDR process is going from uranium hexafluoride that comes from the enrichment plant through to powder granules that we then go on and press into pellets and sinter and so on. So really, the IDR process, we're only interested in what happens in the rotary kiln. So the chemistry is as follows, that's all in your sheet. So all I'm looking for there is just a very brief description of the process where we take hex from an autoclave, we put it into a steam jacket, we pass it through a rotary kiln with a counterflow of hydrogen. A bit of chemistry takes place, all dry chemistry. It's not happening in an aqueous solution, it's all a dry process. And out of the other end we get water vapour and uranium dioxide. A little bit on the fuel cycle, just a couple of sample questions here. I might, for example, ask for different enrichment methods, or I might just ask you to describe one in particular. In this case, it's the gas centrifuge method. So all I'm looking for here is actually not a pretty coloured diagram, it's just a very, very quick sketch showing the centrifuge, the gas being spun round at very, very high speeds. You can indicate that there's a thermal gradient as well, so we've got both a mass separation where the heavier isotopes progressively move towards the outside of the centrifuge, and the lighter isotopes, the ones we want, tend to come to the middle. But we also got some thermal gradients axially, and again we get the lighter stuff tending to move towards the top, heavier stuff tending to move towards the bottom. So the enriched product that we want tends to move towards the top of the centrifuge and towards the middle here. The top scoop is the enriched uranium product takeoff. One stage is never enough. We have to pass it through many, many stages. Not quite as many though for a centrifuge as for a diffusion plant. So I'm asking you to highlight the advantages and drawbacks. Again, just a few bullet points. It's a relatively low maintenance design, very small power consumption compared with diffusion plants, very compact, relatively low capital cost, low operating cost, and very flexible. Very small amounts of material are actually in the centrifuge. Why is that an advantage? Yeah, it's a reduced criticality risk, absolutely. Yeah. Also, if you want to change the enrichment, for example, if you move from one batch to another, the actual amount of material held up in the process is much smaller. So it's a lot easier to change from one enrichment level to another enrichment level if you're operating a centrifuge plant. It's a lot more difficult if you're operating a diffusion plant. What does the Purex process look like? Well, fans of chemistry amongst you will remember the solvent extraction process. All I'm looking for is not a whole bunch of chemistry, just the fact that we've got two different liquids. One in which we have an organic solvent, usually it's tributyl phosphate, a diluent of odorless kerosene, and then an aqueous phase, which is our acidic, our acid phase, our hot nitric acid, in which the fuel and the fission products are all dissolved. We mix them together and we allow them to settle. The fission products remain in the aqueous phase, and the uranium and the plutonium go into the organic solvent phase, and then we're able to separate those and extract the uranium and the plutonium from the process. I think that's it, folks.
Just cut them all up together at the end. Yeah, that's it. What exactly is your council passport again? What is your council passport?
Oh, I'm doing as a personal license. Great to be like a manager at work.
Oh. Where are you working?
Parkland. Lancaster.
You have to go to London to get it. You have to work in Manchester.
You have to do it to your local council. So I'm just going to do it in London so I can keep it.
First, after the introductory lecture, the first popular lecture I think before was on an introduction to reactor physics. And we had a look at nuclear installation safety. followed by an introduction to reactive thermal hydraulics. And some would be disappointed to know that we didn't get as far as talking about departure from nuclear boiling. It was a fairly general introduction to all types of coolant without going into full explain a particular system. Then looked at core design, and then looking at some advanced reactor concepts, fast reactors in particular, and then finished off by fusion. So the exam potentially covers all of those subject areas for my part. And I just note some points here from each of the subject areas that basically you need to consider in your revisions. So starting off with the physics, we talked about atomic structure, with the Rutherford Bohr model of the atom, with all the mass concentrated in the nucleus, with a cloud of electrons walking around the outside. So there's basic definitions of things like the nucleus, nucleons, which are the component parts of the nucleus, the neutrons and the protons which make up the nucleus. We then went on to talk about what happens when we vary the number of protons and neutrons. We get vary the number of protons with different chemical elements. We vary the number of neutrons. We keep the number of protons constant. We end up with different isotopes. We can lump all that together and just call those nuclides. The nuclide is basically defined by the number of protons it possesses and the number of neutrons it possesses. So when we're doing work with chemical reactions, all we're really interested in is conserving neutrons and protons. And that generates nuclides, and then from the proton count we can use the periodic table to identify what element that nuclide actually is. So it's all in the notes, so just read around those initial definitions. We then talked about the importance of the ratio between neutrons and protons, and how this defines the stability of the atom. And one of the figures in the notes was the stability curve, with a number of neutrons along the bottom, a number of protons at the side. And for light elements, we find we need roughly the same number of neutrons and protons in order to bind the nucleus together. For heavier elements, we find we need about 1.5 times the number of neutrons to what we need protons to ensure we have enough glue and a binding force to hold the nucleus together. So this generally means if we split a heavy atom, such as uranium, which has got 1.5 times the number of neutrons and protons, the products that we produce from fissioning that atom, from splitting that atom, will have more neutrons than their position in the periodic table suggests they should have. So generally, fission products are neutron rich. That leads to a particular type of decay, beta decay, which involves a conversion of a neutron into a proton, or maybe even the injection of a neutron from the atom. So we talked about radioactive decays, alpha decays, beta decays, and gamma, which tend to be associated with previous decays, and the relationship between those, where those various decays happen, and where the atom actually sits on that stability diagram. The other concept which we introduced, which I'm sure Abby talked about a lot more, which talked about radiological protection, is half-life, and we were interested in half-life in terms of its role in nuclear reactions, things like breeding reactions where we get uranium-239 decaying into neptunium-239 decaying into plutonium-239, and also the production of delayed neutrons in reactor control. So half-life is a very important concept, the idea that over a given period of time, half the initial unstable